This is joint work with Pieter Kleer and Guido Schäfer. And well, since Yanan talked about the additive case, I only have to go quickly through the basic setup. So we have a set of agents A, and each agent comes with a private cost. And we also have a buyer with a budget B, and this buyer has a valuation function defined over all possible sets of agents. Now, so the picture looks something like that. It's a procurement auction setting, right? We have a buyer with a budget. We have our agents that you can think of them as selling an item or offering a service, and they have private costs. And well, in the previous talk, the valuation function of the buyer was additive, but this doesn't have to be the case. In fact, here, the valuation function V in general is a non-negative, non-monotone submodular function. Of course, the objective is still the same. Find a set of agents S that maximizes the value of the buyer while not exceeding the budget. And we want to design truthful, budget-feasible mechanisms with strong approximation guarantees. And strong here means like constant factor. Well, now, truthfulness means that, well, no agent has an incentive to misreport their cost. And, but budget feasibility is, well, it's not exactly correct what I've written there, because the mechanism pays the agents in order to ensure that it's truthful. So what we want to bound is not the sum of the costs, but rather the sum of the payments. Right. So as Yanan mentioned, this whole line of work was initiated by Singer in 2010. This is a nice, clean, single-parameter mechanism design problem. And what is nice about that is that Meyerson's lemma guarantees that it suffices to find a monotone algorithm, and then there's a unique payment scheme that, paired with this algorithm, produces a truthful mechanism. The problem here is that these two objectives, truthfulness and budget feasibility, in a way contradict each other. And in this setting, when you go beyond like additive valuation functions, even exponential truthful mechanisms are not obvious. And what makes things worse is that there are no general techniques here. So the only widely applicable approach, even for more well-behaved valuation functions like additive or monotone submodular, is using a very simple greedy subroutine. So before coming to that, let me say a couple of things about the related work. The last decade or so, additive and monotone submodular valuations have been extensively studied in this setting and also in settings where the agents come online or there are combinatorial constraints. And there are a few works that go beyond submodularity and even beyond monotonicity. But in general, for non-monotone submodular objectives, what we know is an exponential time, high constant approximation mechanism. And that is due to Bay, Chen, Gravin, and Lu. Now, so what is the general approach in the literature? Well, the vast majority of existing constant approximation mechanisms boil down to the following. Either output the single best agent or output a simple greedy solution. And this greedy solution in general is inspired by the two approximation algorithm for knapsack, where we sort the agents according to their marginal contribution, their marginal value over cost ratio, and then pick them up to a certain point, exactly as Yanan explained. And in general, we carefully pick a threshold up to which we choose, but this is the high-level approach. And the problem here is that for non-monotone submodular objectives, this greedy approach fails badly, and and this is also the case for many reasonable variants of this approach. And fails means that either the approximation ratio is very poor, or we have like the monotonicity of the mechanism or the truthfulness breakdown. So, nevertheless, our main result here is that there is a polynomial time, universally truthful, budget feasible, constant approximation mechanism for general submodular objectives in the value query model. And that's a lot of terms, so let me go through a few of them. So first, let me remind you that a set function is called submodular if for any sets S and T, where S is a subset of T, the marginal contribution of any I to the small set is larger. Therefore, it captures this diminishing returns effect. Also, in the value query model, we assume that we have Oracle access to the evaluation function via value queries, meaning that we assume that there is a polynomial time oracle where we ask about a set S and it returns V of S. And finally, we say that a randomized mechanism is universally truthful if it is a probability distribution over deterministic truthful mechanisms. So in our case, truthfulness is not truthfulness in expectation, but this stronger notion. Okay. Now, I'm not going to go into detail in that, but a nice thing about our approach is that it generalized beyond the plain setting. So for instance, the same result with a different worst constant. And by the way, this O1 there is something like 500. So, this result can be extended to the online secretary setting where the agents arrive in a uniformly random order. And it can also be generalized to a setting where we have combinatorial constraints, in particular where the feasible sets form a P system. And in that case, we show an order of P approximation mechanism. And in a sense, this is the best, the most general result that we could hope for constant approximation, in the sense that once we go to the broader class of non-monotone XOS objectives, we can show that for any non-trivial approximation, we need exponentially many queries. Now, this is an overview of a simplified version of the mechanism, and it's still, we follow this pattern with some probability return the best agent, and with some probability do something greedy. And I'm going to just focus on this part, which is the novel algorithmic idea. We call this simultaneous threshold greedy, and you'll see why in a minute. I will not go into details about the approximation factor, but I will discuss the monotonicity, therefore the truthfulness, as well as the budget feasibility of this part of our mechanism. So assume for a minute that the maximum value of any agent, the value of any agent is small compared to the value of the optimal solution. And by optimal solution here, I just mean the algorithmic problem, right? Submodular maximization subject to an APSA constraint. So assuming that no agent is particularly special, there is an algorithm, this simultaneous greedy, that given an estimate of the optimal value, outputs a set that approximates opt within a constant factor. And moreover, it's sufficiently simple and it uses a monotone allocation rule that when paired with the threshold payments of Myerson's lemma, it results in a budget feasible solution. So there are a couple of things here. First, let me start with the red phrase. Well, how can we do that? I mean, we can do this easily via sampling, and this is exactly what we do. We sample half of our instance, we solve there, and then we use this information in order to run our mechanism on the other half. And a crucial thing here is that this algorithm greedily builds two solutions at the same time. And this is important for two reasons. Well, why two sets? Well, it's not hard to see that if we run a simple greedy procedure for a non-monotone submodular objective, it's easy to get trapped to a bad local maximum, right? Then Gupta et al. In a 2010 Wine paper showed that we can avoid that by running greedy multiple times. But of course, if we do that, we have trouble with monotonicity and truthfulness. So this is why it's crucial to do this at the same time, to build the two solutions simultaneously. Now, so at the very end, we get a statement of the form that, well, with constant probability, at least one of the two sets that we built contains a good solution. And if this is not the case, then this is because the best single agent was good enough to just output her as a constant approximation of it. So, okay, so we start with our initial set of agents. We randomly split it into A1 and A2. And what holds here is that with probability at least 1/2, both A1 and A2 contain at least roughly 1/4 of opt. And let's say that we are in this good scenario that both sets have enough value. And then, indeed, if we approximately solve on A1, and I just mean use one of the known mechanisms for submodular maximization subject to an abstract constraint, for instance, Kulik et al.'s algorithm, we do get a good estimation of the optimal solution in A2. Right? So, but so far this is just what we do before our greedy algorithm. So let's forget about A1 and focus here. So forget about A1. We just have a good estimation of the optimal value, and we know that we have enough value in A2 as well. We build two solutions, S1 and S2, each one with its own budget B, and let's call these budgets B1 and B2 respectively. By the way, I use this notation as a shorthand for the marginal value of I with respect to Sj. This is pretty standard. So what the algorithm does is it iterates through the agents once, and now its agent I is a candidate either for S1 or for S2, whichever maximizes her marginal value. But being a candidate doesn't mean that she will be added to the set. She will only be added to the set if two further inequalities hold. Let's take a better look. So the first inequality says that agent I is cost efficient with respect to set Sj. And you can see that especially if you solve for the marginal over the cost, it just says that the marginal value over the cost is above some threshold. And the second inequality says that we have enough leftover budget. And why this is relevant, because, well, this quantity in the middle, it turns out that essentially it is a take it or leave it offer to the agent, right? So at any point we say, well, are you happy with this payment, right? And if yes, we add the agent to the corresponding set. Otherwise, the agent is rejected once and for all. And so that's why it is important that this is less than Bj, so that we have enough money to pay for this agent at the end. Because it will turn out that these are exactly the threshold payments of Meyerson's lemma in our case. So, okay, we built the two solutions, and at the end, we have S1 and S2, and everything else was rejected at some point. Okay, so what is relatively easy to see is that this is a monotone, that this is indeed monotone. And well, why is that? So let's say some agent was added to S1 at some point. So this means that when we checked this, this was true. So if this agent reports Ci prime instead of Ci, and Ci prime is lower, well, this is still true. In fact, something stronger holds here. Anybody in S1 or S2, by lower her bid, not only stays in S1 or S2, but cannot affect the solution at all. Right? So here goes the monotonicity. And so paired with threshold payments, this becomes truthful. But still, I haven't said what the output of the mechanism is. So in the end, we return the best of S1 and S2. Or to be more precise, we return the best set that is hidden in S1 or S2, because since this is our objective is non-monotone, it could be the case that there is a good solution contained in here, but both S1 and S2 look bad. Right? So essentially, we approximately solve in here and there, and we return the best solution. Now, coming to the budget feasibility, as I said before, it turns out that the payments are exactly that. This threshold of 10B over opt of A1 times the marginal value of the agent the time she entered S1 or S2. And the way we update the residual budgets B1 and B2 is such that we end up budget feasible. And to see that, notice that every time I is added to Sj, what we do is we subtract essentially the payment, the final payment of agent I, right? So since Bj never becomes negative, we know that if we sum up all the payments, they never exceed the initial value of Bj, which was B, and therefore the final, both S1 and S2 are budget feasible. So, okay, I will conclude with some directions for future work. Now, our mechanisms are randomized, and this is crucial, in fact. And designing deterministic mechanisms for this setting has been elusive from the very beginning. So I find this is a very interesting direction. And beyond that, I mentioned that our best factor is like 500. Of course, the algorithmic counterparts of these problems have much nicer approximation guarantees. Can we somehow close the gaps? And well, if not in general, I mean, can we do it at least for like nice families of objectives like cut functions? And well, if not, this means that there are strong negative results to be proven here, right? So for instance, can we show a separation of randomized and deterministic mechanisms with respect to the number of queries we have to ask, right? So if you're into this kind of things, there are many interesting questions here. So I will stop here. Thank you very much for your attention.